Hello, everyone. Can you guys hear me?
Yes.
Great. All right, so welcome to 520, ITS 520. So welcome back. So today we're going to continue with our discussion of machine learning. Let me switch over to some people in the chat. All right, so just letting everyone in right now. All right, so I think everyone's in. Trying to find, okay, yeah, all right. So let's switch over to the Moodle, Brightspace, I mean. All right, so you guys should be seeing Brightspace right now, correct? So I just wanted to go over one thing in Brightspace. I've basically broken up the class into 6 parts. There's really 6 main areas, and I want basically all of these 6 classes to get about the same amount of time. So I just want you to know that. So if you look over here, intro, WEKA, performance metrics, those 3 modules are one part 1. You know, they're kind of the basics of everything that we're going to do. So today we're going to look at a program called WEKA. And basically, by the end of the day today, you will be able to say, oh, I can use machine learning. So you'll be able to do some things. After that, the second part is data sets, NumPy arrays, data scraping, and Twitter. So these 4 modules have to do with features, getting data, processing data. And you know, any machine learning class needs to include, this is nothing to do with the algorithms, but it's just getting data and getting it ready. So we're going to explore that. That's part 2. Part 3 is supervised learning, sklearn, naive Bayes, and KNN. So just some basic, I would call it like the classifiers, traditional classifiers, getting started with classifiers. Then after that, we have tensor operations in TensorFlow, the TensorFlow low-level API, and TensorFlow 2.0. Kind of look at the contrast between the 2. That's another module. This would be machine learning, big data kinds of things. So we're going to talk about, you know, big data issues, you know, millions of records and all that. GPUs. And then reinforcement learning. So that's, even though I only have a module right now, that would get, I wanted to get as much time as the supervised learning algorithms. And then the last part will be unsupervised. So I'm going to leave unsupervised and singular value decomposition and recommender systems for the end. Okay, so that's kind of, I believe it was, I counted it is really 6 parts. And that's really how I want to run 520 this semester. As I said, we're going to take a top-down approach versus the bottom-up approach that I usually take in 530. So we're going to start, you know, in you know, that way. Should be pretty fun. Okay, so I want, you know, I love structure and things like that. So I just wanted to go over that. Are there any questions before I begin, guys? Are there any questions? And I'm trying a new computer here, so I'm hoping, you know, I'm hoping nothing breaks. Okay, so let me know certainly if the audio is not working, the volume. All right, I believe I'm recording. That's you guys can confirm. I think it says on your end that it's recording, so please let me know if you see something strange. All right, so I have a couple of slides today, and then we're going to get into the WEKA program. Okay, thanks. So let's get into the website first. So now I'm sharing the website. I'm going to the course website. Sometimes I post things on my website. It's just easier for me. You know, I super easily can just add things here. So the thing that has of note I already posted the videos here for last week. This is what we're doing this week. So you can see here, basically, I'm going to do a lecture the first hour and 20 minutes. And then the second hour and 20 minutes is going to be just getting into WEKA. So I think I told you guys last week to please install Anaconda and the WEKA program. Both of those you can install on Windows, so we can get up and running on Windows pretty quickly. So I'm gonna go over them today, kind of demo, that kind of thing. All right, so that's the plan. And then here, as you can see, next week on the 7th, it's a holiday. And then after that, we're gonna come back to performance metrics and so on. So I haven't updated the calendar, but now I have a pretty good, clear structure of what I want to do this semester with the class. So, it's just a matter of not falling behind with time so I can hit every topic. All right, so the other thing of note for you guys, we're still working on the Scholar. Mitch is working on that, so more to follow. And then here, so you're going to need these data sets for today. So I'm going to give you your very first homework assignment. It's going to be pretty easy, given that you have a 2-week break, right, because of that Monday. So I'm going to assign to you a homework. So what I'm going to do today is I'll talk about Fisher's iris. Fisher is like the classic data set in machine learning. He was a scientist in, early 1900s probably. And he developed a data set. So I'm going to use Fisher's data set. It's very tiny. I'll talk about it. All right. And as you can see, you can download it. We're going to talk about data formats, CSV. Right now, I'm only going to cover, once you have a data set that's ready for machine learning, what do you do with it? How does that work? But the next phase, part 6 of the course, would be basically how do we go from crazy raw data all over the place, pictures of cats, network data, airplane sensor data. How do we go from all of that to creating a data set that looks like these data sets, okay? So the two classic data sets, that you will see quite a bit in books, in everywhere when you do machine learning, are Fisher's iris and the MNIST data set. So Jean LeCun developed MNIST, I believe, for the Postal Service. So the Postal Service wanted to, people write zip codes, right? They write zip codes like, whatever 46323 is Hammond, where the campus is, I think. So people write these digits, and they wanted to build a sorting machine that kind of just looked at the numbers and could sort them, right? So Jean LeCun developed this MNIST, which is a data set, or otherwise known as a corpus of handwritten digits, right? From 0 to 9, obviously, all the digits that we have, because those are the numbers in the zip code. So that's really what we're going to explore today. We have that data set, and we're going to, you're going to, I posted these files. They're kind of big. I mean, not big data big, but they are way bigger than IRIS. So I believe MNIST is probably around 70,000 samples or so. So we're obviously, in any machine learning class, this is a very, this is intro. It's meant to be your first machine learning class. So I'm going to start with that, and I'm going to touch on the WEKA program. I like WEKA because I've been using WEKA. Like, honestly, it was, when I learned, we didn't have all the things. There was no TensorFlow or anything like that. So WEKA was much more popular back then, and it was super easy, and it provides everything that you would need. So it gives you a really nice picture of what machine learning is. And so even now, I believe that we have all these tools. WEKA is still quite good at getting us started really quickly. And now they've developed it so that it can interact with deep learning and other things, but we're not going to be using that. I'm not a big Java fan. So, all right. So anyway, that being said, these are the data sets. As I said, we're going to download Fisher's iris. and then you guys can, you know, also download it, and then, but that's going to be during the second half of the class. So if you haven't done so already, make sure that you have WEKA, Anaconda, and these data, at least Fisher, downloaded by the second half. All right, are there any questions about anything that I just said? No questions? All right. So I think everyone is in here right now. Let me do the course participation just really quickly. Take a picture of, I'm gonna take a picture of all of you guys, the attendance. Okay. All right, so I have the picture now. All right, okay, so let's go now and just share the slides. I have these slides. Can you guys see the slides?
Yes.
Yeah?
Yes, we can.
All right, so this is, you know, just now kind of more formally, I'm going to go over the topics of machine learning. I think most of you already know, I already gave kind of a big, you know, context, motivation, and big picture. So now let's just get into the terminology and proceed from there. So this is the introduction. As you can see, I'll be using my little pen here whenever I need it. Okay. So, you know, the learning outcomes of a machine learning class, students will have a better understanding of machine learning approaches, you know, how to tackle different problems, right? So that's why we're gonna have unsupervised reinforcement learning. And then right now, today, we're mainly going to do supervised learning. And I already introduced, so I already gave that concept last week, right? So what was supervised learning again? What was the definition of that? Anyone? Supervised learning?
I mean, in supervised learning, the algorithm learns on a labeled data set, you know, providing
Right.
an answer key.
That's right. We have labels, right? We have information. So we have a picture of a cat, and then we have a label that says that's a cat. Very good. All right. So that's what we're going to focus. Initially, students will have a better understanding of features. Okay, features are the way that we take an image or text from, you know, natural language processing, or as I said, you know, information from sensors, and you know, we need to represent that in some way, right? In a way that machine learning algorithms can understand, because they only understand numbers. They need to find correlations, either patterns in the data or correlations between those features and the labels. Students will have a better understanding of data sets. So today will be our first, you know, attempt at using data. As you know, data is, as you will learn, data is a lot of work. 70% of your time usually will be spent on cleaning the data, improving the data, and so on. One of the reasons why I do Twitter in this class is that Twitter is so noisy. There's so much stuff in there that you don't need. So you really have to figure out how to filter out all that noise. Okay, this should say to solve problems in general. I missed that there. So just students will have a better understanding of the need for machine learning to solve problems in general. We're not gonna just focus on cyber, but we're gonna focus on many other areas. Students will have a better understanding of the difference between deep learning and machine learning. Definitely, that's something that, you know, I don't believe that you should teach a machine learning class without devoting some time to deep learning. And so, I already told you guys that deep learning is neural networks, right? And they're just one algorithm within machine learning, but they're very powerful and very good at processing large amounts of data. And so students will have a better understanding of big data and how it relates to machine learning and how it, it presents challenges, right? So those are really the objectives of the course. All right, so some terminology, you've heard me say it, it's important. Machine learning, deep learning, features are pretty important, and big data, okay? So, dealing with massive amounts of records efficiently. All right, some of the tools that we're going to explore, you can see that here. So this is still like taxonomy or terminology, but these are all tools. So if you're, you have a toolbox, right? And then you want to have as a machine learning person, or an applied data scientist, you want to know how to use these tools effectively. Okay, so we're going to start with WEKA today. Obviously, Python we'll be covering all semester. I will introduce NumPy. I'm not going to spend too much time on pandas. This is a class covered in 265, a new course here in the program. I will definitely cover sklearn as I introduce the very basic machine learning algorithms. I will be focusing on TensorFlow. However, you should be aware there's PyTorch, right? Cafe, I think, and so on. There's a few other ones out there, and some people like PyTorch. I'm not saying it's not great. I just, I believe, TensorFlow is backed by Google, right? And so Google is pretty competitive, and they have a lot of resources, a lot of money to invest in this. And so they're doing a lot of development. I always feel like they're doing a lot of development and then others are catching up. And so you want to kind of follow the leader. But that can change, that definitely can change. So you want to be aware of that. And it's just a choice. And, in the future, others will, and in the future, others will come. And so that's why you have to be cognizant of the code. Remember that these libraries like TensorFlow, you have basically a GPU. And the GPU, you're going to write your code in C++, but the GPU needs some kind of a library that helps you to interface with the GPU, because if this is an NVIDIA GPU, like an RTX 2080 Ti or a P100, which are the most state-of-the-art right now. And then from here, people will then, usually Python, as you know, is an interface to C, C++. So when you develop a library in Python, right, then that library gets compiled into C. So really, that's the connection right there. But right now, libraries are, TensorFlow 1.0, 2.0, PyTorch. But you could build your own, right? So if you ever want to just, you feel like doing things, you can create your own library, call it, whatever you want. And then the key is you have to follow that pipeline, right? So you have to C++, CUDA, and all of that. You need to learn how to do parallel programming, which is a different kind of programming. A lot of the programming that you have done probably is sequential, event-driven or sequential coding, kind of, but all CPU-based. Now with GPUs, it becomes parallel. And so this will be some, part of that discussion when I get to big data. That's part of it, right? So that's what I'm going to talk about. So right now, though, before we get to big data and TensorFlow, we're not really looking at GPUs. So really, we're looking at CPUs, sequential machine learning. So things that may not scale as well. Although if you have a good laptop, 32 RAM, a good processor, I don't know, 12 cores or something, you'll be able to get things done for sure. Just don't expect to be able to tackle the things that Google or Facebook can. You know, just to give you a contrast or a you know, a picture of what they have, the kind of research that they do right now, they have a computer using 8 GPUs. At so it's basically you know, a big rig kind of a machine that has a motherboard that supports 8 GPUs. I mean, this machine requires special cooling, as you might be aware, and these GPUs are the most advanced P100. I think these are called Titan, if I remember correctly. Titan GPUs right now, and so that's what they have. So that you know each one of those Titans costs like 5,000, 4,000, 5,000. All right, so you know that's the kind of computing power that we're talking about for big data right now, and the kind of research that they do, at least on GPUs. And that's just if you look at the papers that they wrote maybe in 2017. So right now, who knows what they're doing. Another set of tools in machine learning is called Hadoop and Spark. So I should say, we will not cover these two topics, okay? These are not two topics that I'm gonna cover in this class. My focus with big data is on GPUs and that type of parallelization, but there is another type of parallelization, you know, via CPUs. For some of you that took the old 470 class, that we have here, it's something similar to that. So that's, you know, creating cluster computing. Although that class is no longer required, it is coming back as a Hadoop and Spark class. So if you guys have an interest in that, you can talk to Professor Tae-Hoon Kim. So this is certainly, as you put words in your resume, right? Those words will definitely come up. Now, Hadoop and Spark are not just for processing, not just for the classification or the machine learning algorithms part, but they're also very helpful at storing the data and organizing the data. So you need there's a lot of tools that I'm not mentioning here just for dealing with the data, massive amounts of data efficiently. So for some of you that took my 372 class, you might remember I covered Hadoop from the point of view of system administration, just configuring that in Linux in 372. So that gives you kind of an idea, but we didn't really analyze any data. All right, so just wanted to stress that this is an important set of blocks that is not covered in this class. And the reason being is that those are really, as I said, cluster CPU-based parallel computers. So instead of having one GPU machine with 8 GPUs in it, now you're talking about 30, 40, who knows how many computers like the ones we have in the classrooms, all CPU based and all networked together, right, as a cluster. All right, other tools or terminology, obviously AWS. As I said, you know, you have to pay for this one. We are working on Scholar, so hopefully we'll have that this semester as an experiment that we're doing with West Lafayette. Should be free. And then finally the processors, right? So the processors that you will see out there, I'm missing one here actually. Can anyone tell me which processor I'm missing or architecture? I'm missing one. Let's see if anyone knows. See, here I have GPUs, CPUs. There's something called TPUs. If you don't know what that is stands for tensor processing units. So a tensor is a matrix or a vector of any rank or dimension, or any dimension, I should say. And so TPUs are, I think they're only an innovation of Google right now, and they have TPUs on their cloud that you can basically rent. And then there's cognitive processors. Cognitive processors would be chips that are just designed to do machine learning. They're specialized. They're more of a research area, but there's a few out there. An old one called Cognimem. The CM1K it's called. And that one, you know, it's good for, you know, the research basically. And then I'm missing one thing. Which one am I missing?
Is that an NPU?
It's not an NPU, no. Yeah, that might be something else that I don't know about. But
Yeah, neural processing unit.
Neural processing unit?
Yeah, like I mean, it goes by the name by TPU, so TPU and NPU could be the same. So.
Oh, okay, all right, yeah. So it could be this one, but I'm missing one more. Anyone else? It's an important one, actually. Guesses? Has anyone heard of FPGAs? Anyone? All right, so the FPGAs are a type of microchip or computer chip that is configurable. Even though it's in the hardware, you can actually configure it a little bit as well. And so it's sort of like saying I have a CPU or a GPU, but I can play around with the architecture of it. The company that I know is actually spending time on these is Microsoft. I've noticed that Microsoft is doing some research on FPGAs. I guess they figure, you know, TensorFlow or Google has TPUs, everyone's using GPUs, might as well try something else. So they're experimenting with FPGAs, which seems pretty interesting. All right, I haven't really, honestly, you know, it seems more like an electrical engineering focus. I haven't had much time to look at FPGAs, but you know, there's probably some good research out there. All right, this is some of the terminology and the tools. And so I've stressed the things that we will be covering in the class this semester. Are there any questions? All right, so the emphasis today will be on WEKA, the WEKA program. So I really want to get started with that quickly. So let me just go through some of the definitions more formally. So what is machine learning, right? So it's methods for predicting, detecting, or grouping data samples based on a model. So you will usually be building a model, and a model is just some mathematical equation, a calculation. So for instance, if I have, let's imagine just visually, I have data that looks like this, right? And I have data that looks like this. Now we all remember when we took, you know, our classes, Cartesian planes in high school and everything, we had data like this. We have a, you know, a F1, let's call it F2 axis, and we can plot everything here. So a machine learning model that is a classifier, that is to say, it's some kind of a function that allows us to say, hey, given, you know, given, let's say this square, intuitively, you guys see that square, and I ask you, what do you think? Do you think that square is more like the class of the circles, or that square is more like the class of the x's? What would you say?
I think it's none of the above.
None of the above. Why?
Because that's itself standing, those circles and those crosses.
It's not a circle, you mean? Because it's not a circle?
It's
Well,
the
it's
odd one
like
out.
it's not a circle. Yeah, it's not a circle.
Yeah, let's imagine it's a question mark. It's whatever. But if you look at it in the context of the Cartesian plane, just intuitively, like if you were like a little kid and you look at circles and you look at x's, and I ask you, based on the information you have in front of you, do you think that question mark is more like a circle or more like an X?
Neither of those.
Neither of those.
Circle?
Why circle?
Because it's more geometric shape based instead of just like lines.
No,
Okay.
I think it's close to the circle. We
It's
can
closer
see
to the circles, right? That's really what I'm saying. If you think in terms of the Cartesian plane, in the Cartesian plane, you have distances, right? 1, 2, 3, 1, 2, 3, right? So you have all of these positions. And so in terms of that, you put everything in a point, in a reference system, a coordinate system, And now if I ask you, now let's say that I put another one. Now I put this other question mark over here, another sample, another thing that I have placed in this space. What would you say about this other question mark? Would you say it's more like a circle or more like an X?
More like a X.
More like an X, exactly. And that's, you know, it's one, machine learning is one way of thinking. And this is the way that we think of things. We represent them in these vector spaces, and then we decide what something is. So in that case, you guys were just saying, you know, you came up with some kind of a distance function. You said, well, if I calculate the distance, that's kind of long. Now, if I calculate this distance, it's kind of short, right? And that's one way of doing it. Another way of doing it is, a more general idea is to come up with a model. So let's say that I create that. A model is nothing more than that. You see that in a two-dimensional space, this is 2D, because it's a Cartesian plane of two axes, you know, F1 and F2. Then in that space, I create a line. And now I have a rule that says, if the question mark is on the left side, it's an X. If it's on the right side, it's a circle. Do you see that, guys?
Yep.
Right.
And that's it. That's pretty much, I'm done.
So basically the model helps in, you know, distinguishing where it belongs.
Yes, exactly. The model is, you know, it's a function, right? It's a line. We know that, you know, a line y equal mx plus b, right? You know, we learned that in school. And so
Yep.
given an input, right? That's the input. Given some parameters that we need to learn, we can determine what something is. Okay, there are various ways that we can do that. But that's the general idea. I don't want to get into this part right now. Just intuitively, I want you to understand that. Now, one important thing is this M, or W, if you want to call it W, and B determine the line. That is to say, like the shape of the line. So for instance, I could have another set of, I could have, let's change that M now to W. And let's just say I have one set of W1, B1. And that gives me this line. So it's that line. You see that? But I could have yet another set of W2, B2, another set, and that gives me a line like that. So instead, I could have this line. Do you see that, guys? Does this make sense?
Yeah.
Right.
Yeah, so I can have, you know, line 1, let's call it, or line 2. Those lines, the position of them is determined by, you know, these parameters, W1 that you learn, because this is the equation for a line that we have learned. So all that you're doing in machine learning is you want to predict or detect, right? Like the question that I had, I have a question mark. I just want to know, is it an X or a circle? That's pretty much it. And grouping would be like unsupervised. And you want to do that based on a model. So what is that model? Well, that model, first of all, needs a context. All right, let's create a Cartesian plane like this one. Okay, a two-dimensional space. Okay, we have the data. We can represent the data. How do we represent the data? Each one of these is a sample. For instance, it could be an image of a cat. Each one of those X's is an image of a cat or a dog or a rabbit, you know, whatever. And then we need to represent it in this space through what is called the features. And then once we've represented it in that space, now we need to figure out which model we're going to use. So usually you want to use linear models. Okay, linear models just means that we're using straight lines. And so now we need to set up a very brief set of equations, and those equations look like that. Do you see that? Okay, give me a sec. Right, can you mute your microphones? I'm going to mute someone, but mute your microphones if you can. All right, so once you define that we're going to have a line, We're going to have a line, a linear model. So if I'm going to throw a name out there, something called logistic regression. Logistic regression, boom. Always lines. But which line? Because if let's say that, so now comes in something called, how do we train the model? So the model, we need to give it information. It needs to, in a for loop, learn, try things. I'm going to try this, I'm going to try that. So a good intuitive way of thinking about that is it's going to repeat that process. It's going to learn a set of weights and a set of W's and biases, which are these. And those represent the shape of the line, okay? So for instance, let's say I'm going to try L3. And L3 is going to be W3, B3. That's a set of parameters that feed into here, right? That determines a new line. And the line looks like that. Do you see that line, guys? Versus the line for L1, which was more like this. Just intuitively again, which one of those two lines do you think would be a better model? Just intuitively, just by looking at the picture.
L3.
L3? So this is L3, and this is L1. Which one do you think might be better?
L3.
L3. You think L3? Why would L3 be better? You think? Remember, our goal is to separate zeros from x's, right, as best as possible.
I think it's L1 because it's separating clearly x's and zeros.
Yeah, and actually, there's a good way of thinking about. You're right, but there's a good way about thinking about it. So let's erase L1 and just leave L3. If I have a question mark there, this model would say that this is a 0, correct? Because it's to the right of the line. Is that correct?
Yep.
It could be an X.
Yeah, because one of the X's, fall under right-hand side of the plane.
Exactly. For instance, when I give it the real X, it's going to say it's a 0. So that's an error. Does that make sense?
Mm-hmm.
Whereas if I do this, and now I classify all my samples, all of them are in the right place. So let me just give you an even crazier example. Let's call it L4. It's got W4. Maybe this one will be more obvious. And that, for whatever reason, I mean, the Cartesian plane is infinite, right? Draws the line over there. Do you see that? Now remember that I should say that this data, the x's and the circles, are samples from a population that supposedly should follow some kind of distribution, right? So the assumption that you always make is you never have the population, right? You never have it. But you want to have a sample of the population, that enough of the data that you think that now you've captured the distribution of the data, right? So what that basically means is that if this was the training data like this in this area, right, then in the population, you will never find a circle over here. It will be an extremely rare event. You see that? So the model that we built with the line there represents the population, or this distribution. If I pick L4 and the line is over here, first of all, it's outside of the distribution, right? It doesn't seem consistent. Just by looking at it, it seems strange. What about this classifier? This classifier, if I say something like this, then it'll say it's a circle. And then if it's to the left, it's going to say it's an X, right? It's going to say it's an X. So in this case, basically all of these would be misclassified. And because of that, this is very wrong. Does that make sense, guys?
Yes, sir.
Right.
Yes? Questions? No question. So ultimately, what we're doing is when we're looking at a model, is it depends on the type of algorithm. There are different kinds of algorithms. This is just the most common type, but basically, you're going to train the training. So basically, you give it data during the training phase, and during the training phase, it's learning a model. Given the features which represent this space called the vector space, the model needs to learn something, like a function, like a line. And what is that line? So we can have infinite lines. This one, that one, this one, this one, that one. Look at all the lines. But you optimize the process based on some criteria. In our case, the criteria will be to minimize the number of errors in our training set, okay? That will be the criteria. So if I choose that one, I have errors. If I choose that one, I have errors. If I choose this one, I don't have errors anymore. But it could be that we do have a sample like that eventually in the population. It's just a little bit too close. So what we want is a criteria that also says, you know what, create like a margin, right? And the line that maximizes, for instance, that margin. You see how I just went from a model that just puts a line where there are no errors to now another model that puts a line, but there's an additional constraint that says, put a line there, and by the way, I want it to be like a really thick line, you know. So it's really like to the left and to the right of the line, given some epsilon, 1 and 2, right? Or 1, rather, it's just 1. Given some epsilon value, there should be still no errors, because look at this. I could pick a line that's like this, right? I pick that line. If during training, there will be no errors, correct? You guys see that? Do you agree, guys?
Yes, sir.
All right. But it seems just odd a little bit, because there could be eventually an X there, right? And so just given that, you know, how the things look. So some models just do that. And that's just like it's called a classic linear model, like a linear regression. Other models will do a line, but now they provide a margin. You see that? Now, with this margin, does the model still perform as well? Or are we going to have errors now, given that we have the margin? We have errors, right? Because even though the line here did not, using that line, we still had, you know, no errors. The fact that we're also constraining and saying, hey, there should be no errors with that line within a certain margin, right? And so here, the 0 will be just within the margin. You see that? And so when you're training and optimizing, you're going to say, you know what, even though I thought that line was good like that, when I try the margin, I realize that it's not great because I do have errors. So what do? Do this. Because now, see, the margin is still there, but now there's no error. So ultimately, what I did by adding that additional constraint is I ended up with a better model. You see that the line is in the right place. So I was able to like rotate. If you notice, what I did is I rotated the line. Is that clear, guys? Does that make sense?
Yes.
Are there any questions about that?
I don't think so.
All right, no questions. That's good. So I just want to stress then, you know, why. So this is important just to illustrate why we have different algorithms. Same problem. Same problem. Okay. I'm going to call this one logistic regression. That's, you know, that's new to you. Don't worry about it, but it's just called logistic regression. What does that one do? Just a line like that. No errors in the training data. I give it this sample, no error, this sample, no error. So this minimizes the number of errors. Okay. This is meant to be about the same data, right? Same data. Now, with the margin, E, I get this model. Still a straight line, but notice that by adding that margin, I change things. This one is called support vector machines. It's a very similar model to logistic regression. It ultimately, really, one of the main things, it has a few other tricks, but one of the main things is that it provides that margin. Do you guys see that, guys? So what I'm trying to illustrate to you right now is because you're going to hear me, oh, now run this algorithm, run that algorithm. We're going to probably talk about between 20 and 30 different machine learning algorithms. And I want you to understand that there's just little subtle differences that make them different. Got it? What about this problem? Now notice this data is a little bit different. That might be a little bit too tight there. Can I use a straight line to build a model for this data set and have no errors? What I mean by that is it has to be a straight line, right? So it has to be a line. So can any one of you place a straight line in that data somehow that separates x's from zeros and leaves everything, all the zeros on one side, all the x's on the other side? Is that possible?
No, I don't think so.
No, it's not possible, right? Because if I do that line, I get some errors, right? I get that zero. This zero here was in the wrong place. I try like that. Got some zeros over here, right? So what would you suggest in that case then? What would you try to do then? We need another shape of a line, right? Like a curve. You see that? I needed a curve for that. It's no longer a straight line. I could also, there's little tricks, like I put a line there, and 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 a line there. You see that it's pretty much the same thing. That's a whole bunch of little lines makes a curve. As much as in calculus, like a whole bunch of little bins creates a curve, you know, or anywhere else. So do you guys get the idea? So in this case, if I'm going to build some kind of a function here, right, it's no longer linear. And that, you know, we can call it a neural network. But ultimately, it's just a line. We're putting a line in there, only now it's not a linear line. And so easily here, I was able to show you 3 different algorithms that we're going to talk about this semester. I may not talk so much about SVM, but basically the same problem, and you can see why we have different algorithms. Okay, it's just because we want to minimize the number of errors by using different tricks, like straight lines versus curvy lines, and so on. Okay, is this concept clear, guys?
Yes, sir, very much.
Excellent. All right, so let's go back then. So that's what I wanted to illustrate there as far as the model. Okay, as far as the model. So intuition, right? I wanted to give you the intuition as to why we have the algorithms and so on. So the model then, as I've said, must be learned with the data. So we're going to give it data. Usually we're going to take a lot of data and we're going to split it. We're going to take 80% of the data. You will learn how to do that today. 80% of the data for training, 20% of the data for testing. You can do other breaks. And that's just going to be one day. Why do we have, the training is obvious, right? We build a model, we build a line, the curve, whatever. Why do we need to leave 20% of the data for testing? What would you say? What is that for? I mean, didn't we already train the model? Why do we need to leave 20% out?
What was the question again?
we have, so I'm going to take a data set, right? Let's say a data set of 100 samples. 100 samples. But I'm going to take 80% of it and I'm going to train that model, those parameters, and leave out 20% that I'm calling for testing. What do you think that's for? Pretty much everything we're going to do for the first few weeks, I'm always going to say, you know, all right, take your data, split it, 80% train, 20% test. And then what do you do with the 80%? You train the model, right? So now you have a line. And then why do we need, if we already calculated the line, why do you think we need to leave 20% out that we haven't used in the training? What do you think we use that for? At 20%.
To make sure that your model is actually accurate, or
Very,
else because
good,
I mean,
very good answer, because yes, we trained the model on some data, but remember, and this is key, right? There's the population, and then there's the sample that you've taken. Maybe this is, you know, 1 trillion things, and you actually have a very decent 2 million, you know, samples, but it's still only a fraction of the entire population. So what a model does, and I'm just going to use normal distribution here to kind of indicate distribution. So let's say a model just, you know, in this population, there is a distribution. That is, you know, in the normal distribution, you just say, okay, there's going to be a mean for a certain value, a feature or something, with a variance, right, or standard deviation. So that's what you want to capture, hopefully, with the very small sample of data that you've taken, but just be aware you may never be able to capture the entire population. You see that? So if your model's really, if you have very tiny amounts of data, just like a dot there, you're more, I can't say, you know, I cannot generalize and say, well, you know, this or that's going to happen. The only thing I can tell you is, in all likelihood or in all probability, the smaller your sample is, the less likely it is to capture all the details of the population. Okay.
Professor Ricardo, that 20% will be a random or?
It's not a random, it's just a number. There are other ways. There's something called cross-validation that's a little bit better. We will talk about that later. But for now, we're just discussing 80 and 20%. Oh, the data is random. Is that what you mean? That we pick the sample?
Yeah, that's what I'm saying. 20% will be a random?
Yes, yes. Sorry, I understand what you're asking me. We pick the data randomly, yes, as much as possible. Does this concept make sense, guys?
Yep.
So that's why we have 80% and 20%, right? The idea is 80% just looked at some data, we built the model, and hopefully, so the idea in a perfect world, as you said, we picked randomly 80%, right? The circles. And then the other 20% randomly, you see that? Should be fewer. So we picked these, right, for testing, and the other ones for, let me just color them. Okay, those are for testing randomly, and the other ones are for training also randomly, right? So in a perfect world, we built the model with the circles, the clear ones, right, 80% of the data. And then we take the little squares, which are the other 20%. Notice that they're not, they're mutually exclusive. So they're not, you know, if you train with this data, you cannot test with it. You have to use another set. And so the idea is that by doing this process, it's like you're checking yourself. Okay, you're checking yourself and saying, oh yeah, you know, I trained it with 80%, and then when I run it on the 20%, it still does well. And so that's when we're going to get into measuring performance, okay? And the fact that we're trying to measure how well our model performs. Another way of looking at this that might make it even clearer is that, you know, we pick that, you know, from there we pick for training, and then from there actually we pick for testing. But it turns out that if you look, we're missing a very big chunk. So we may have captured the dynamics of that area, but not the entire population. So when we apply our model to things like there, it might do okay. But once we start applying it to there, you know, you're going to be in trouble. So that's like you know, that's like, you know, talking about fashion, but only looking, you know, if somebody who's doesn't know anything about the world and they want to learn about fashion, but they only look at the countries that have no winters. So they have, although they think they've only looked at that, they really are missing an entire piece, which is the countries that have very strong winters, for instance. And so their model is not very good. It cannot generalize well to the entire population. Okay, so that's one of the general concepts, one of the biggest problems that you will encounter in machine learning. That's why big data, right? The more data you have, the better, hopefully, your model will be. And that's why you always, you know, machine learning models are very specific to a task, a very specific task. So they're not like super AIs that can solve every problem in the world. They actually only solve very, very specific problems because of this issue of generalization. Are there any questions about this at all?
Yes, Professor. Just one question, like, can we train the test data, or it just has to be the training data alone?
So you have, remember, we're trying to figure out this line, right? You know, should the line be, where should the line be located in the plane? So the parameters, the weights and the biases to determine that line will be learned by looking at the 80%. You want the 80% because you want more, as much as possible. But you
Right.
leave out a good chunk, 20%, for testing, for instance. But this could be, let's say, out of 2 million, this could be one, I don't know, 20%. I think it's like 1.6 versus 0.4. You see that?
Right.
And they're completely separate. So you don't use the same samples.
All right, got it.
Got it? Okay. Sometimes you also need to play with parameters, other parameters that you want to learn in your model. So in that case, you might do what is called a three-way split, where this is train, this is validation, and this is test. And that just helps you, it gives you, before you arrive at the final testing set, you can look through the validation one to just kind of improve the parameters a little bit more. All right. Okay, so methods can be geometrical, which is pretty much what I've been discussing, or not. They could be probabilistic. We'll see those. That's why I will cover naive Bayes a little bit. So it's a little less intuitive geometrically than most of these geometrical ones. A lot of foundations of machine learning have to do with this Cartesian plane and vector spaces that you learn in high school is very important. And then the models are based on either distance metrics, which we haven't discussed yet, or linear boundaries, right? And I talked about linear boundaries when I talk about these lines. All right. Move on. So why machine learning? So there's too much data, right? So we got to learn, you know, you don't program the code. It's not like if this, do that, if this, do that. Instead, a way that you can think about it is that the if statements are being learned by data itself. So you have algorithms to teach the algorithm how to make decisions. One of those classic examples is decision trees, which is called J48 in WEKA. And that's one of the algorithms you will use today. as well. So the decision tree is a little bit different because instead of being kind of like this intuitively, and you can always represent it graphically, but it's going to be like, I'm going to take, I have several features, F1, F2, F3, and they represent cars by price, horsepower, and fuel consumption, right? And so you're going to say, well, if I want to buy a car, what's the most important feature for me? Probably fuel consumption. So let's say it's F3. So you're just going to say, if miles per gallon is 24, less than 24, you know, then it's going to go in that direction. So it's greater than 24 or less than 24. And so now you start creating these decision trees or decision paths that ultimately allow you to arrive at some objective, like a class, the prediction of the car. Okay, so you want to say if a car will be highly purchased by people. Okay, well, it's possible that fuel consumption is the most important feature for people. And so the model should learn that somehow, but the way the model will look is kind of like this, like a tree. So don't worry about it too much right now. We will look at decision trees in a little bit more detail later on. We'll print out a graph actually of a decision tree. Okay, so building the models by hand is labor intensive. And so we know that we can use nowadays computers to automate this whole process. Okay. So what is big data? So that's another concept, just kind of formally define it. I've talked a lot about this already. Lots of data, terabytes, petabytes, just huge. And, do you think the amount of data available in the world, or let's call it the digital universe, do you think it's going to eventually stop growing, decrease, or continue to grow? What do you guys think?
Continue to grow, I believe.
Grow, right? Do you think it'll grow slowly, or do you think it'll grow exponentially?
It's going to grow exponentially because the population is growing.
And the population of technology is also growing, correct?
Correct.
Yeah, so nowadays, I mean, think about the Internet of Things, and all that. They're going to generate more data. Everything you do nowadays on your computer, on the browser, is collected by someone. Amazon, I heard recently that they were somehow developed a device that uses your voice, your everything, a whole bunch of sensors to know how you're feeling, basically. And so I guess they can sell you products better. So it's just gonna continue to grow. And so and that's the thing, because the data keeps growing, people want to use that data. People want to think about how many millions and millions of dollars are being spent on the current election, for instance. And that money, they're trying to analyze people. They're trying to find out, okay, what's that little area in a state, in a district where I need to go and invest my dollars, because you can't invest everywhere. And so it become, it's mind-boggling, the business. Google, just to give you an eye-opening statistic. Google, everybody knows Google. Right? How does Google make money? I mean, at least Amazon, they sell you products, correct? But Google, how does it make money?
By ad revenues.
Ad revenue, right? They don't sell you anything. I mean, you might have a subscription to YouTube, but otherwise you use the search engine, So they generate all of it from ads by collecting your personal information. They do that. I heard a statistic that Google right now has so much cash. So think about it. That means that the model actually works. They make so much money, and they have so much just cash on hand that I think the statistic was that they could buy 2 Airbuses, the company Airbus in Seattle that makes the airplanes. They could buy 2 of those. That's how much money they have on hand. And so you can imagine it is a big business for them and for others too. And so there's a huge demand for it, and that's why they keep pushing it. And so that's what big data really means, right? It is really, really large. It's so much data, in fact, that a single computer with 8 RAM or even 32 RAM today, and the latest CPU with 12 cores or threads or whatever, it still, you know, cannot do it. You really have to have either clusters or GPU-enabled computers or some other solution. So you need more powerful computers or several computers working together. So I talked about this. 2 main approaches, basically. Parallel CPU, so that's 470 Hadoop, right? Or more like a GPU, one in parallel, right? So that's, you know, what we're talking about this semester, 520, 530. All right, so that's really the 2 solutions. As I said, there's others. Microsoft is doing research FPGAs, but I think that's only at a research stage right now. I would put TPUs, Google's thing. They get a lot of marketing with that, but I think it's just like a GPU, only optimized. And then maybe in the future, anyone know of anything else? Any other approach to big data? No? Maybe in the future, quantum computing or something, but you know, we may actually never, at least your generation may never see that become a reality. All right, so so what is big data? We talked about that. All right, so now let's just, you know, go over, I'm gonna wrap up, you know, just summarize what I've been talking about with a few little graphs, and then we'll take the 10-minute break, and then when we come back, we're gonna get started with the WEKA program. So machine learning terms, we have supervised learning, right? Usually these are classifiers. So you have, as I said, you have your data, you split it, 80% for training, 20% for testing. That will be what we do for a while. And then as we progress, you're gonna learn other things. But for now, I don't wanna there's so many new terms, right, that I don't wanna overwhelm you. So let's just stick with that. So basically then you build a model. Remember the model, intuitively you can always think. What's the model? The line, right? So we build a model, and then now from the test set, right, we give it a, we apply new test samples to the model, right? You can see that here. And then that predicts a value for a given, so that would be, what is this one, right? So this one is the same, white, and then we get a prediction, and then we evaluate performance. And that's just accuracy. So that's as simple, the simplest evaluation is in the test set, you're going to have X, right, which is your data, and that's going to be associated with a label. And then you have another, so it's X1, another one, X2, L1, L2, right? And those are the real ones. Now, it usually turns out that the label is called Y. Sample could be a vector. And that's, you know, then we have the features, we have the labels, and we have, let's call it the predictions. So in the predictions, you're going to have a Y1, Y2, but let's call it Y hat. So those are the predicted ones. So the way that you evaluate performance is for sample 1 and for sample 2, I'm going to take Y1 and Y hat 1, which is the predicted, right? And I'm going to say, are they the same? So was it, if it was a picture of a cat and that was the label, did my system predict cat? If it was a picture of a cat but the system predicted dog, then you have a misclassification. Does that make sense, guys? Are there any questions about that concept? All right, no questions, it seems. That's good.
I got a question. This Y test will come for the 20% or from the 80% or both?
Say that again.
The Y test,
Y test, yeah, is the predicted value. Yeah,
will that be coming from the 20% or 80% or both?
from the 20%.
Okay,
Because think about the logic. We built this model with that data. And now we are testing the model with this data, and the model predicts that. It's the prediction.
okay.
So basically, the Y test is an input from X test and the train data as well.
Which one, sorry?
I mean, the Y test is it taking input from?
It's not an input. That's a good question. Y test is an output. It's an output of the model.
Right.
Not an input. An input would be this. So the way to look at it is, I take X test, give it to the model, and the model gives me an output, which is Y test.
So I guess it is a little confusion. Since we are giving 80 and 20% to our model, how is this model going to distinguish just the 20%?
I mean, this graph is not meant to be an algorithm, right? It's just a general, I guess where I see your confusion. So don't take this as the algorithm itself. It's just meant to be a brief overview of this. Really what would happen is you have train data first, before you do anything. Train the model. Right? Done.
Right.
We're done. In a separate, completely separate, you got your test data. You feed the test data into the model. And the model makes predictions. So for instance, here, now the one thing that I should say is that when you're building the model, you always give it X train, Y train, right? You give it, samples and the associated label. In this section here, the next step, you only give it X test, and the model will predict, guess, Y test. You see that? The model will predict it. But this X test, when you're evaluating, could be associated with a Y real, right? And that's how you measure the model is you're going to say, well, given X test, the model predicted Y test, and I also happen to have Y real. And so now I can make a comparison to see if my model is performing well or not. Is this clear now?
Yep.
So that's the idea. Don't worry, the graph was meant to be very high level. So it's just kind of showing you a few things, but this will become very easy when we do it in WEKA, for instance. You will load the train data, run it, then the test data, or do the split automatically. But just keep in mind, it's two things. Part one, you do it, let's say Monday, done, and then you come back on Friday and do this part two. They're completely separate, but they're using the same model, which is the model that you learned in the previous phase. Okay?
Okay, so got it.
All right, great. Unsupervised, this will be the last topic that we will cover this semester. I'm just going to give you a quick one here on clustering. Clustering is basically, I don't have labels. Notice, all I have is this. You see that? They're all X's. So I can't build a line because, how would I know the parameter? But intuitively, what can you tell me about looking at this picture? What can you tell me? Just intuitively, what do you see?
It can be grouped.
It can be grouped, right? It seems like there's two things, two obvious things, two groups, and that's called clustering, or two clusters. Cluster 1, cluster 2. Okay? So that's unsupervised. Don't worry, that's like our last topic this semester, so we'll get to it. So other terms in machine learning, features, right? We'll learn about that, how to create our own features. Data sets, obviously, we'll start learning about that. As I said, data pre-processing, you'll have to do a lot of this. Cleaning the data, you'll see it. It's very labor intensive. And then performance metrics, I showed you today, just accuracy, but we're gonna practice that quite a bit. And I will have a lecture on that the next time we meet. So what are some of the algorithms out there? There's naive Bayes, decision trees, random forest, KNN, linear regression, logistic regression, neural networks, support vector machines. Neural nets become deep learning, and that just brings even, you know, a ton of algorithms. You see that? And this is just a few. All right, there's other ones, but these are the most important ones. Usually they're the ones that I will talk about. You'll learn how to write the code for that from scratch, how to write the code for that from scratch. And then using libraries, you'll learn how to do the other ones. But we will explore all of them. As I said, I'm not going to get into each one right now. I already gave you the intuition, right? Sometimes it's a straight line. Sometimes it could be a straight line with a boundary. And sometimes it could be like a curve, a polynomial or something. Okay? So those are the algorithms. And some of these are implemented on the CPU, and then others are implemented by writing the code in parallel. And so that makes them more efficient for the GPU. So what is deep learning? Just, you know, kind of to wrap up, deep learning is a neural net, but with multiple hidden layers. So whereas, you know, a neural net would have this view where this is the input, this is the output, and you're learning, oops, and you're learning something there, right? The model, let's say the line. Deep neural nets have that basic structure, but they have additional layers. So don't worry about that for now. Just wanted to throw that in there. We will come back to this topic later on. So I'll talk a lot about this later. Okay, so what is the machine learning pipeline? You'll usually hear me talk a lot about that. And the machine learning pipeline just means if you're going to apply. So what is applied data science, or what is this thing you're learning? Basically, what you're learning is you want to apply AI-based or artificial intelligence-based techniques to multiple types of problems. That's really, obviously that involves some kind of automation and things like that. So usually that's going to involve a sequence of steps called the pipeline. All right, and the pipeline will be, generally speaking, get the data, right? You know, collect your data, Twitter data, for instance. You want to find out for the election, right? You know, who's going to win, Democrats or Republicans? Okay, well then, you know, what are people saying? Can you create a poll via Twitter of what people are saying? That, you know, you start to define your problem. So you identify, okay, I need some data. I'm going to use Twitter. It's Twitter data. But then you have to go in and you have to pre-process the data. That means you have to format it. You have to clean it. You have to extract the features, right? Then you're going to represent the vector space model. That just means that Cartesian plane, right? 2D, 3D, Rn, right? Any dimension. Then once you have all of that, you move on to selecting the machine learning algorithms. Usually what you'll do is you'll try a few, you know, a baseline one, and then from there use other ones and so on. And finally, performance metrics, accuracy. We're going to learn other terms like precision, recall, F measure, and so on. The confusion matrix. All of those will help you to better evaluate your algorithms, okay? But this pipeline is what we're going to be doing all semester. Data formats. Yeah, so because it's 3:20 right now, this is a good stopping point. Data set formats, given that in the next half, we're going to start WEKA, and we're going to be using files in CSV, but there are other data types like ARF. So we'll pick up here, okay? So we'll pick up here. So what I'm going to do is, so I don't end up with such a large video, is I'm going to go ahead and stop here. I'll come back at 3:31 again. Meanwhile, I'm going to save this video. All right, guys? Questions before I sign off? We'll be back in 10 minutes.
Okay, no question.
No questions. All right, great. So I will close here and come back to this slide in 10 minutes.